All right, so I'm gonna go over a couple of techniques, a couple of papers that me and my co-authors have published on the matter of trying to change the state in which we kind of have sequence-to-sequence model, transformer-based models, but we kind of don't really change the resolution of the sequence, and that results a lot of redundancy. So we're in the business of tracking that redundancy and trying to remove it. For motivation, let me go just very briefly for something like this. We got really lazy by having convolution nets that are super good models for extracting hierarchical features from the data. Right? You apply them, you can have models that downsample your input, and it just works. And it has been working for years. Now, for sequence-to-sequence models, we don't really have something that is analogous. And I don't want to say that nobody has developed that we're just ignorant. What I'm trying to say is that there's like no go-to solution. And we're just stuck with the state in which the input resolution dictates the output resolution. And this is how we live. And it's funny when you look at speech cognition models in particular, because speech has the qualities of both image and audio. And it's like template architecture that has been like emerged throughout the years. It's like you take a small convolutional encoder that downsamples the sequence, and then you slap on a sequence-to-sequence model, and you don't change the resolution at all. And so for transformer models, and right now let's start focusing on GPT style, so autoregressive models, people find those redundancies that I told you about all over the place. So the input, right now it's a tokenizer. It dictates the resolution that you keep throughout the entire model. Right now we are in the state that you typically have 128K subword units. It's growing a little bit. Just recently it used to be like 32K in flagship models, but it can only get you so far because you quickly will exhaust memory by increasing the number of tokens, and you will have diminishing results. Nonetheless, I have put here a couple of ideas where people track the redundancy and how really clunky this resolution is for the model. Apart from aesthetic reasons, aesthetic meaning that, well, subwords don't really well align with words and higher level concepts, there are clear performance reasons. When you have shorter sequences, things get faster. And you will have quadratic complexity in attention, be it training or be it inference. So reducing the length of the sequence really helps. And for some time, I had the impression that there was this argument circulating around the community that, well, perhaps it's not that bad because the more tokens you have, the more compute the model is investing, and maybe it's going to help the accuracy. Right now, it doesn't seem the case. Like the advent of reasoning models, that shows you that it's really the quality of the thinking of the tokens, not really the amount of the tokens that matters. And so first, I would like to focus on this hourglass transformer paper. It's one of the many architectures that try to do that downsampling and upsampling, and it's going to be relevant to our later research. So it works great for images, and we also tried it for Wave2Vec2, so for speech, it also worked great. And it does fit the bill of something that tries to downsample the sequence and then upsample it back in order to make the output. So this is the image from the original paper. It looks a little bit scary, but let's go left to right, and it's super simple. You start with the stack of transformer layers that is blue. Then you downsample with a fixed stride. Then you run another stack of transformer layers on a shorter sequence. This is like this yellow-orange color. And then you can keep downsampling in order to reduce the length of the sequence, but somewhere later on, you need to upsample back in order to output the original resolution. And so we arrive at the first paper that I would like to tell you about. It introduces the model called dynamic pooling transformer, and it's basically an attempt to apply this hourglass architecture, but with a dynamically changing stride of this pooling operator that adapts to the data. And we try to develop this specifically for language, for character level language models. So in a hope that it would find like nice primitives and then build higher level abstractions. So the architecture looks kind of similar to the original hourglass transformer. You can see that in the pooling and upsampling blocks here, the sequence, the segments have different lengths. And the length of the pooling segment is dictated by boundary predictor. This is on the left. This is this right mysterious block. Now, the boundary predictor is tasked with predicting just zeros and ones, and those are later interpreted as either boundaries or not boundaries. And you proceed like in the hourglass. You have vanilla transformer layers. You downsample. You run the tokens again through the transformer layers, and then you upsample, but you need to upsample it with respect to original boundaries. Also, you might think of this from the like a routing perspective, in which only selected tokens that fall on the boundary get to go through the entire network, and the rest just skips the middle layers through the residual connection. And here I'd like to make like a side note that it's, for me, it resembles kind of the mixture of depths paper, in which every token can be like routed around a number of layers. Again, this is like a nice way of showing that you can exploit the redundancy in order to speed up your model. For DPT, the analogous plot would look something like this. A small difference here is that in the DPT, whenever a token passes the stack of all layers, the representation is more rich because it has been pulled with the preceding tokens, right? The preceding tokens not just skip layers, but they contribute to the later token that go through all the layers. Now, how to design the boundary predictor and how to know when to pull the tokens. So this is our original motivation. This is this observation that whenever you got a character level language model, you can observe a spike in entropy whenever you start a new word. And that's kind of obvious, kind of sane, because this is where you get the most uncertainty. Once you start producing the word, the uncertainty drops. So it made sense to us to try to align those tokens that traverse the entire network, like kind of think that those should align somehow with like word boundaries. That would be nice, right? So based on this observation, we had like 4 attempts to build a good boundary predictor. The first 2 I would call like baselines. A white space one, when you are in the English language, you can just take white space and then treat it as a training signal and then train your boundary predictor in a supervised way. Also, you can run like a tokenizer. We used sentence piece, and you can try to train your model on that as a training signal, so sentence piece boundaries. Another 2 were more interesting. The first one is self-supervised, so we kind of try to predict those entropy spikes with a heuristic. You cannot really take them as is, because you need to somehow detect if there is a spike or not. But a simple heuristic, when you look at a couple of preceding tokens, and if the one that you're looking at has the highest entropy and it's a spike, that seems to fit the bill. The last one was purely unsupervised, and we tried to learn the boundaries with Gumbel softmax, so predicting 0 or 1 for every location in the sequence. Now, just to have a quick look at the results, more results are obviously in the paper. The fixed pooling, which is like the pure hourglass architecture, nothing dynamic, it doesn't perform well on language. The unigram baseline is very strong. It was kind of hard to beat. White space baseline as well. It's not shown here for clarity. With the Gamble softmax end-to-end trained, we had like mixed results. Some of models came out really great. Some were like kind of unstable. And we concluded that in order to make this work, we would need to pay like more attention to what is exactly going on there. But the results overall were encouraging. The entropy one is not here. It's on the paper. I would say it was pretty robust. Not as great as the white space or unigram, but strong, robust results. And performance-wise, it saved like at least two to something X in latency and in memory. But when we went with higher shortening factor, meaning higher compression, we get diminishing results. This is because the entry layers and the last layers, they don't change the resolution, so you pay full price for having those layers anyway. Now, I need to mention byte latent transformer. It's hanging somewhere here in the room. This paper came out later, but was really a good attempt to replicate this and enrich this and engineer this at a higher scale. Our experiments were like lower than 100 million parameters, and the byte latent transformer went to the 8B scale, which takes a lot of effort to execute this at this scale. And a similar entropy-based model worked very well. And I'm really glad that somebody did this comparing to the Llama 3 size model. Another interesting mention would be the HNet, which came out very recently. And it uses similar ideas to try to hourglass the architecture. I would say that the main idea here is to try to make it in a way that you could actually apply it multiple times and build a hierarchy, hence the name. Two mentions that will be relevant later on, or two ideas here. There are many ideas in this paper that make it like rich. One is that instead of pooling, the authors have chosen to discard tokens, and they say that it worked better. The other one is smoothing. So when they built like those downsampled representation, they try to like make a smooth transition in between them in order to help the training. Now, the original DPT paper, that was 2022, just before the ChatGPT frenzy and everything that followed. Right now, we are in kind of different world. It changed a little bit. That I would call software 3.0, following, I think, Andrej Karpathy, who I think coined this. And I would switch the narrative to the world where we right now have like foundation models, and nobody really gets to train them, with the exception of the large companies who put enormous amount of resources into producing those models. Most of the people find themselves as the users of those models, which they can program and maybe optimize. And from this point of view, it starts to make sense to look at how to make those models faster. So not really optimize the training, but optimize inference. And in order to optimize inference, a nice way to reduce the resolution is to look at KV cache. Now, without going into much detail, KV cache is bad for performance, and the longer your sequence is, the more the sentence that it's really KV cache that dictates the latency is true. What I mean by that is attention is memory bound on reading the KV cache in order to perform the computation. The more KV cache you have, the less everything else that is going on in the model, so feed-forward layers, the less it matters. So, and because reasoning has become more and more increasingly important just because of the advent of the reasoning models, long reasoning chains produce large KV cache. So optimizing KV cache became more and more important. And of course, there are many ways to skin a cat. I would say that there are two extremes right now, and I think most of people would agree with this view, that the first extreme is pure transformer model, when the KV cache size grows linearly with the sequence length. On the other extreme, you get SSMs, where you have constant memory. And both of those worlds have their own pros and cons. There is, however, a middle ground where I would say the hybrid models live, and all the research that goes into strong KV cache compression. This is something that you would like to strike, like this middle ground. So compress KV cache so strongly that it's actually a viable alternative somewhere between. Now, let me talk to you about the second paper in the bunch. It's called Dynamic Memory Compression. And so in this paper, we try to take the lessons learned from the DPT paper, but then try to adapt it to the KV cache compression problem and to the state when you have a foundation model that you would like to optimize. So think of it as trying to take a foundation model and then slowly kind of ease it into compressing KV cache. This is why I put this here, this graphic that shows you that something slowly morphs into other object. Why morphing exactly, analogy, and why this attitude? Those models are very expensive to train, and whenever you have this this idea that you would like to make like little steps, playing with those models gets much less expensive, because you don't need to break the model, then reassemble it in order to see the result of your experiment. You can just quickly see where the things are going. So just to ground the world that the second paper lives in, we would like to now pull the sequences of keys and values for the attention layers. And the sequences of values, the compression of those, mirrors the compression of keys. So it's like one compression scheme for every key value pair. Now, the funny thing is that you can apply that locally inside a attention layer, and the input and output remains at the same resolution. And also, you no longer need to upsample. So no worries about upsampling and replicating the boundaries on the other side of the model. The best way that we found to actually talk to people about this paper is to first show you the end product, so how it should work during inference, and then try to slowly introduce the training regime. So on the left, you can see a vanilla model and something that should resemble KV cache in this model. And in every step of inference, you just append tokens to the KV cache. Now on the right side, I will show you the operation of a DMC KV cache layer. And it's unrolled in a time, right? So every row is going to be another time step. So let's say we start with a single token. The model has something akin to a boundary predictor as well. It outputs a binary decision alpha. Now, if alpha is 1, we say no boundary, and then keep pulling the tokens, but inside the same slot. So it doesn't expand the size of the KV cache. And then let's say in the next step, you also see boundary predictor saying 1. You keep accumulating. Then you hit a boundary, and you reserve a new slot, and you start accumulating there. And so on and so forth. Now, in order to apply that to a generation regime, and we took the average pooling that is similar to DPT and kind of rewritten it in a recurrent form. So those equations might not look that clearly, but if you try to untangle them, z is like the normalizing constant when you try to average a couple of things. It's just the count. Alpha is 0 or 1, so it either zeroes out the previous key or previous value or keeps it. And then if you just try to write down a couple of examples, what happens in this equation, what you get when you've got alpha equals 0 equal 1, you just keep either pulling or zeroing out. So this formulation has two nice properties. One is that it actually can be rewritten in a way that allows you to use parallel scan. And this is this nice trick that SSM use in order to calculate something that looks like expensive because it should be calculated left to right, but you can use efficient algorithm that does reduction that calculates it in log time or log steps. The second trick is that whatever I shown you as the end product, that looked like something that uses if-else clauses. But if you interpret it as alpha being like a multiplicative constant, you can execute it on GPU, just using arithmetic operations and no if-else instructions. This is GPU friendly, in other words. Also, during training, we can relax alphas and allow them to be like fractions in between 0 and 1. Why would we do it? We would do it because we would like to have nice gradients and we would like to optimize a smooth function. And this is very smooth and very nice to optimize, just believe me. And also, this is something that I would say is kind of akin to the idea in the HNet, where I try to smooth out the neighboring representation. So during training, we allow alphas to be like fractional. And this way we can have those intermediate states, which make the optimization much easier. Also, I should mention that in order to fully recreate the inference setup during training, we kind of need to keep all intermediate steps of the accumulation, but kind of block the access to them. So this, I try to kind of show it on the left, that Q5 query at step 5, it should really have access only to the fully accumulated keys, because during inference, key 0, key 1, those would be overwritten by key 2. So we need to somehow recreate the situation during training, and we do it with a mask for the attention. But because we are in the world where alphas can be fractional from 0 to 1, the mask also uses like fractional masking. And now to the results. The funny thing is that you can apply this algorithm to every layer and actually every head independently, and it will give you different results just because every head demands a different pooling resolution. And now looking at what happens in, this is Llama 2 13B during training, and you can see layers on the horizontal axis, heads on the vertical. These are sorted vertically by the pooling rate. The dark pixels here are the heads that chose not to compress the sequence at all. The white ones compress 15 or more times. Basically, those heads don't like to have any KV cache at all, as far as I'm concerned. And then there's a large number of heads in the first half of the model that like to have some kind of resolution, some form of KV cache, but not the full. Also got a couple more of those heat maps. The bottom one is for Llama 2 70B. This one is kind of interesting because it features GQA. So you've got those much less heads, so much less redundancy. And it's funny because the model chose to either have full resolution or very much compressed heads. I should also mention that the first, say, 4 heads, depending on the heat map, you would think that the first layers, which would subvert word inputs, shouldn't really look for, right? Those should basically focus on reassembling words out of subwords. So you expect local interactions mainly. They need full resolution. I would say it's like artifact, because we try to pull we kind of messed with that mechanism. So that was us not thinking it through, like how it should be designed for the first layers. So those layers don't like to pull, probably because those layers like to look at individual tokens to reassemble like higher level concepts. Some results, I don't want to stop here much, but just to show you that on the left, the solid lines show MMLU score as you progress during training. And as I promised, in the morphing slide, it doesn't really fall. You can see small drops, but it's nothing spectacular. And on the right, you can see some results, also in comparison to train-free token eviction methods. And because those are train-free, we don't expect from them so much accuracy. But the takeaway message here is that, well, 4 times compression mostly preserves the accuracy, and I say it's safe. With 8 times compression, you see small drops. Depending on the downstream tasks, 1, 2, 3 percentage points. So 4 times, I would say it's mostly free of drops, 8 times small drops. Here is like a quick performance plot. It shows you that when you compress the KV cache and save a lot of memory, you can choose to spend the budget that you saved. Either you just don't add new examples to the batch, you keep the batch size fixed, and then you can expect lower latency, or you can spend the memory that you have saved on putting more examples in the batch and then having better throughput. So you've got like this Pareto frontier, and you can choose whether you would like to spend your savings on latency or throughput. And also this plot here is made for like small context. So this is why the latency change is small, but for longer context, you would see much better latency improvements. And so it will be all nice and rainbows, but the model kind of was expensive to train, even though we say it takes a fraction of the tokens needed to train the model from scratch. For foundation model, that's still a lot. And we kind of needed 44,000 training steps in order to train those Llama 2 models to 8 times compression, which is a lot. And we didn't get to experiment with them much. And I guess that would be like the first obstacle towards wider adoption of these kind of algorithms. Also, another caveat when you compare it to DPT is that during training, you keep the full resolution, right? You need all intermediate accumulation steps, so you don't reduce the resolution during training. That makes every training step of DMC a little bit even more expensive than the training of the vanilla model. And so let's fix it. The third one, dynamic memory sparsification. And this one is very recent. We have released this paper in June this year, early June. And we tried to fix whatever we thought was broken with DMC. So we kind of like to make it faster. Also, draw from the ongoing research that the community is doing on KV cache compression, which is really much focused on token eviction and sliding windows. Those two ideas really are like prevalent. And it all started with the question, do we need pooling at all? And how much accuracy we would lose if we would take out pooling? So turns out that we will not lose any accuracy at all, and if it's going to be better, but there's one key ingredient for all this to work, and this ingredient is delaying the decision to evict a token. What I mean by that? Let's say that at time step 1, and again, I'm going to show you how the algorithm unfolds in time during inference. Let's say that at time step 1, the boundary predictor says 0. For me, that's a vanilla model behavior. I'm not doing anything. Now let's say it predicts 1. For me, it means evict the token, but I'm going to wait number of steps before I actually execute it and remove the token. Let's say for the time being, the number is 3. and I'm just going to train a model that always waits 3 time steps. If you're attentive, you will immediately recognize that this creates a sliding window behavior where you keep a sliding window of size 3 in which you're not touching the KV cache, so you're not messing with the KV cache. So let's follow the algorithm for a couple of steps. The decision variable is 0. You're not doing anything. You're shifting the sliding window. It's like virtual sliding window, like nobody is programming it explicitly. Now that key 2 has fallen out of sliding window, I'm evicting it. It's like something that I do manually, sort of, because it has been scheduled for eviction. And turns out this works really well. And you might think that at the very last step of this toy example, alpha 5 would be better to decide about the eviction of K2. And that's not the case. Why it's not the case? It's because K2 and alpha 2 have been derived from the same hidden representation. They just one linear projection away. And it turns out it's much easier for the model to sort of encode that information. This is something that we think is going on here inside key that is going to be evicted. And now the model has a couple of steps to extract all the relevant information from that key before it's going to be evicted. Also, you might think that I'm trying to game you, and it's really not working well, maybe, because, well, with sliding window, you can have like 1K, 2K, maybe 4K tokens, and it's kind of easy to game the benchmarks and hide that the algorithm is not working well. Well, we get a lot of benchmarks with window size 16, and it works well. And for me, this is a large shift in thinking, because all the, at least the majority, I would say, token eviction papers, they do eviction by trying to track tokens during their lifetime, looking at the cumulative or whatever attention score, and then try to silently remove the tokens that nobody is looking at anymore, in the hope that it's not going to change the output of the model, it's not going to change the attention score, the distribution of probabilities. Here, that's completely different. Here, we are expecting that the information, if the token is going to be useful for the model or not, the information is already in the token from day one. And we're going to just wait a couple of steps. The model should implicitly be hinted, because it predicted from the same representation that the token is going to be evicted, that is no longer going to be needed, and we're just going to drop the token. So right now, I guess you're striving for a ablation when I'm trying to do like immediate eviction. So alpha 5 decides about key 2, and the delayed eviction where alpha 2 decides about evicting key 2, but a couple of steps in the future. So it's a small ablation with the 1B model, Llama 3.2 1B, and different window sizes. The downstream task is GSM 8K. It's kind of sensitive. The most sensitive that we had for Llama 1B. That's why we are using it here instead of some aggregation of scores. This task was like that, the most difficult one. And you can see that even with window size 16, well, the algorithm, if you use delayed eviction, it's going to keep pretty high score. And it works all across the board. With window size 0, you default to like not delayed eviction because there is no delay, right? So in the topmost plot, you get only one curve. Also, this turns out to be really data efficient during training. So I said that 8 times compression took 44,000 steps for DMC. Here we train with 700, and it works. And my personal expectation is that less, or maybe even just small calibration would do, because what I think is going on, that I'm really convinced that the information of the token is relevant. It's already inside the token. You just need to expose it. Because, well, within 700 steps, with small learning rate on a foundation model, you get very little training signal at all. So there is no room to make any substantial changes to the model. And training-wise, not much differs from DMC. Well, the main difference is there is no pooling anymore. And what we are left with is just this attention mask. So I'm just plotting it for the sake of clarity. And then you've got this explicit sliding window on the diagonal. And you choose it as a hyperparameter for every run of the training. Now, let me put all of this into perspective. So I've plotted a couple of models here. This is their KV cache size, log KV cache size. And on the x-axis, you've got log model size. Because KV cache for some of those models, so KV cache for those models scales differently with sequence length. So I just have arbitrarily chosen sequence length of 32K tokens, just because for me, that's a good amount of reasoning. Excuse me. Now on the top, you can see Llama 2 models. I would call them like a first wave, KV cache size wise, just because they don't have GQA. So they have the largest KV cache. Then in the middle, you get a whole bunch of models that use GQA. I would call them like a second wave, KV cache size wise. And the trend is not clear if we're going down or not. It seems like we're kind of stuck here. Then you get a couple of honorable mentions. You get Llama 4 and Gemma 3, which kind of interleave local and global attention. Local attention will have smaller and constrained KV cache. Global attention will have, of course, the full KV cache. And on the bottom, you get Nemotron H, which is a hybrid model, SSM and transformer. And I'm trying to convince you right now that if you take a GQA model and then compress, say, 8 times the KV cache, it's going to bring you to the bottom group of models. I really wish I would plot more hybrid models here, but for the sake of the argument, let's say that 8 times or more compression really does make a difference for those models. Another interesting phenomenon is that let's look at the compression heat maps. So something akin to the DMC heat maps that I showed you before, but for DMS. Those right now would be like eviction heat maps. How to interpret those heat maps? Dark pixels or full, so global attention. White, that would be like local sliding window attention. And then intermediate would be something in between. And here, this is plotted for a model with window size 256. And also, in the table, I put a couple of very recent models which try to combine local and global attention, like I said before, in a different ratio. So people try to handcraft the perfect recipe of how many layers of local you should interleave with how many layers of global attention. So let's say every 3 layers of local, then you put 1 layer of global, and then so on and so forth. And if you squint your eyes a little bit, looking at my heat maps, you can see that the model kind of figures out by itself end to end without any handcrafting. And what I mean by that is that you have those very dark pixels and like roughly similar distances in between them. Also, another fun artifact of this model is that because we enforce the compression, and this concerns DMC and DMS, both of them, globally on the entire sequence during training, it kind of learns to first compress a little and then ramp it up as the sequence length grows. And this is because, well, you get lower conditional entropy as the sequence grows, because the more and more context that you acquire, the easier it is for you to make a prediction. So it makes total sense for the model to kind of cheat and don't compress much when the sequence is short. And once you acquire many tokens, then start to compress more. And it's actually beneficial. We don't control it yet. We haven't tried to control it yet, but for me, this is good because with small context, you don't really care about compressing heavy cache anyway. And for longer ones, you actually get more than you pay for. And so I've got like minus 2 seconds left. So let me finish with the hyperscaling theme of this paper, which is like totally different from the compression part, but also super interesting. So this is a very recent picture from a very recent presentation by Jensen Huang. And it kind of, for me, validates that the industry is kind of picking up the inference scaling reasoning idea. And what I mean by that is that, well, in order to boost the reasoning qualities of the model, you can try to scale the inference. And there are many, many ways and many clever ideas that, unfortunately, I don't have the time to go through. But the two basic ideas for scaling up inference that we have tested is sequential and parallel scaling. In sequential, you can just prolong the length of the reasoning chain, let the model talk to itself. There are different ideas, but the longer the model thinks, the more accuracy you can get. And in parallel scaling, you will try to consider like the same, a couple of reasoning chains in parallel, and then try to combine them at the end. And of course, you can have a hybrid approach when you have long chains, multiple chains, and you try to combine them. And so we did a little experiment. We thought to ourselves, like, hey, if long reasoning chains increase the accuracy of a model, but produce large KV cache, and we've got a machine that can compress KV cache, if you combine the two, how that would work? So we took kind of hard benchmarks. We took math problems, questions from science and coding, and we tried to run different setups of parallel and sequential scaling, parallel and width scaling with different compression rates, and then see how it compares to the vanilla model, but also other methods that we think are leading in KV cache compression. So this is like one of the many plots that we have in the paper. Here we compare with Quest, and the metric is the memory reads from the KV cache. And the green one is DMS, and you can clearly see dominating Pareto frontier. And turns out that, well, parallel scaling is better if you would like to pick two, but it kind of unlocks the third axis of optimization right now, So previously with DMC, I told you that you can either pick latency or throughput, but you will lose some accuracy probably. If you can live with it, it's okay. Right now, no matter what you do, you technically win, because the third axis of optimization is actually you can boost accuracy within the same budget. The another plot is with TOVA. This is different metric. So with Quest, we are looking at memory reads because for us, for a long context, it best aligns with the overall latency of generation. If we assume that the model is heavily memory bound on reading the KV cache, the cumulative amount of reads from the KV cache would somehow approximate the latency that you expect. Here we're looking at the peak memory that the model is using. This is different baseline because Quest is not saving memory. So here we're using TOVA as a baseline. And peak memory is also important because when you are considering long reasoning chain, you can run out of memory. And again, we got dominating Pareto front. We tried to quantify the gains across a couple of models. And we came up with the scheme that you try to look at the vanilla model and then the DMS model, and then see the average distance between the frontiers, and then translate it into percentage points that you will acquire. We see the smallest gains on math just because that benchmark is very much saturated. It's 90-something points. But overall, we could gain as much as 10% points on different tasks. And we have been experimenting since. So these results on the last 2 slides are not in the paper. And it looks like 8 times compression, even 10 to 12 times compression can move the Pareto frontier even more. And for the most recent models, this one is Qwen 3 8B. And also another one for Llama Nematron 4B. So to conclude, I have shown you 3 algorithms that, well, on paper, maybe look kind of different, but they have like very common core. I think they share a lot of analogies with other papers. Basically, I was very delighted to see the conclusion that it's better to discard the tokens than the pull tokens in the HNet. This is exactly the conclusion from the DMS. And I think there's still not a lot of research in that direction, and I hope to see more in the coming future. Thanks.
So with respect to the last DMS one, when you had the eviction window, using an eviction window with some compression ratio, but I can imagine that you could have multiple eviction windows for different compression ratios. And that might actually work well because maybe you would have, right, so if you have a high compression ratio in a short window, maybe it's hard to get all the information out of the tokens that you need in order to effectively use them. But if you had kind of like a progressively increasing compression ratio over time, presumably the tokens which are far away from the generation point are typically generating less information that needs to go into the generation point. And so you could have a kind of a compressing ratio which is increasing. So you could have, trying to explain things, but hopefully you get the idea.
It's, as far as I understand, you are proposing to do it even more adaptively.
Yeah, so I'm saying you, instead of just marking things for eviction or not, you have marked for the X2 eviction, X4 eviction, X8 eviction, and you have a separate window for each of those. And so those windows some of the windows can be longer and some of them shorter.
This sounds really like something that we kind of already thought about. So I think you really understood the idea. And I guess there's a lot of room here to experiment. Yeah. I guess that would be like the broadest comment.
Yeah, hi, I had a question. How close is kind of like a DMS adaptation to just being kind of integrated? You can take any LLM, replace the attention layers with that, and sort of run it in VLM, just like a very more productionized sort of system.
Okay. So we plan to release the code. That's a good information. And I guess releasing the code means 2 things that should happen. The first one is writing any code that will run it, but you are kind of far from being optimal in terms of competing with like reasoning frameworks, inference frameworks, and whatnot. The more involved solution to this would be to write kernels or to patch kernels to actually do what you need to do. The good news is that there already exists a kernel that does exactly what we need to do, and I think ByteDance employees have released I'm not sure about the company, but there is a paper from last year that patches flash attention, and they released the code to do multiple kinds of masking. Excuse me, so more masking that the flash attention tool originally allows you to do. And our kind of masking is like one of the cases that they support. So kernel-wise, it's not, I wouldn't say it's 4. And the rest is just preparing the infrastructure for you to actually execute a couple of hundred steps of training. So I wouldn't say it's difficult. With DMC, it would be much more difficult because you need to have kernels to kind of support that polling. And right now, I'm pretty sure the kernels are there.